Hello, my name is Kevin Lindsey. I'm a principal hydrogeologist with GeoEngineers. In today's talk, we're going to talk about a basalt aquifer recharge project in the central Columbia Basin of the Pacific Northwest of the United States. It's a project sponsored by a large farming agribusiness operation, the target of which is to reverse some aquifer water level declines that this farming operation has experienced in recent years. Project team, in addition to myself, includes Phil Brown at Northwest Groundwater Services, Alicia Candelaria and John Travis at GeoEngineers, the hydrogeologists on the team, these three folks, and then Allie Leeds and Brandon Dunnigan at Carollo, who are looking at the water quality, water treatment side of this project. And then we'd like to acknowledge, give a big acknowledgement to the clients, our client managers and staff on this operation for just being willing to try a look at this type of project, which is not something that they would normally engage in. So the project area, it's located within the Columbia Basin, the U.S. Pacific Northwest, essentially this big green blob down here, the states of Washington, Oregon, and Idaho. The farming operation we're dealing with is over here on the south side of the Columbia River in north central Oregon. This is a zoom in of that project area. The Columbia Basin sits between Cascade Mountains to the west, Rocky Mountains to the north, Okanagan Highlands and Blue Mountains to the north and south, respectively. It's basically a large semi-arid intermontane basin that's the sources of water out here are either snow melt off the bounding mountain ranges flowing down these various rivers into the Columbia River, which flows down through the middle of the thing and out to the Pacific Ocean. Or it's groundwater, which is in the green rock, the green pattern here that basically delineates the Columbia Plateau Aquifer System, which is a basalt, flood basalt hosted groundwater system, regional in extent. So looking at this photo over here, this is a true color aerial image. Again, semi-arid is pretty obvious. Green is truly green. That's a mostly irrigated ag. Columbia River coming through the project area right here, a major source, actually the primary source of water. And again, these green circles, that's irrigated water, much of which is sourced off the Columbia River, although some of it is groundwater supplied. The problem and the solutions in irrigated ag country in the semi-arid Columbia Basin, much of it is groundwater supplied, although not all of it. Much of it is also surface water supplied. Unfortunately, many of those groundwater supply wells show this type of hydrograph. Year to year, declining water levels in the wells are declining. Pumping is outpacing recharge, is depleting storage in the aquifers. So the typical solutions for these types of projects, water rights conversion, change in this part of the world, access to the water is controlled by legal system. We just call them water rights. There are ways to change your water rights, change your legal access to water, and many of these interests do explore that, and some of them successfully make those transitions to solve this problem. Another way to go is change your cropping, irrigation, water use patterns to make these declines either less or possibly even stop them by not pumping a well. Those of you who pay attention to this area may have heard of the Odessa region. That's a region many miles north of us here, where these hydrograph trends are being alleviated by turning off wells and replacing that well water supply with a surface water supply. And finally, a third method is MAR, basically injection of a source water into these aquifers to flatten out and hopefully even reduce or reverse these decline trends that we see year in and year out. So the rest of this talk is going to look at this MAR piece of this project because, again, this farm wants to explore MAR in conjunction with the other two to see if MAR can form part of their solution to their declining groundwater supply issues. So this project, basic context, the Columbia River will be the source of water. In Oregon, where this project is located, there are two basic MAR regulatory environments: Aquifer Storage and Recovery, ASR, or Aquifer Recharge, AR. This project falls into the AR category. And as such, its primary drivers are going to be anti-degradation, whatever is injected into the ground to reverse the hydrograph or fix the hydrograph. Whatever is injected into the ground doesn't degrade the native groundwater. And also, access to that water that's being injected is in this part of the state limited to the winter or off non-irrigation season time of year. Which is what it is. So this project then is looking at, first off, testing and building treatment to address the anti-degradation side. And then there we have to deal with an absence of a natural treatment system. We'll talk a little bit more about that in a moment. And then the other piece, of course, is the limited access to the winter, and that's an interesting challenge because most irrigation systems are not winterized, and the irrigation system our client operates is the same way. After all, you don't need irrigation in the winter because nothing's growing. But in the summer, you need it. That's the irrigation season, so that's when the system operates. So, unfortunately, that means the system's not winterized to operate in the winter when we'd have access to water to do the MAR project. Those two problems then combine with some other interesting observations to get to a scaling issue that we'll talk about in a little while. So a little bit of hydrogeologic setting. The Columbia River Plateau Aquifer System is hosted by the Columbia River Basalt Group, which consists of layers of dense, hard, relatively impermeable rock, alternating with layers of vesicular, rubbly, and commonly very permeable basalt rock, and also includes sands and gravels. And basically these impermeable and permeable or low permeability, high permeability layers are stacked one atop another in a repeating pattern of dense, impermeable, low permeability rock, some hundreds of feet thick, then a nice permeable zone, several tens of feet thick, and then another impermeable zone, and so on and so forth. So that's a nice predictable pattern. One stack on one layer, on top of another layer, on top of the same layer, on top of another layer, alternating one after the other. So it's easy to work with from that context. Looking at the region of interest for this project, it's a big system. This yellow boundary is essentially the hydrologic boundary for this piece of the Columbia River Plateau groundwater system. It's a big one. It's 20 to 30 miles long by 20 to 20 miles across. And the boundary is, although we say it's a boundary, it's a fairly diffuse boundary. There's probably water moving across it, both in and out, as well as within it. There are several major fault systems through here, and it's not clear how much those fault systems actually affect groundwater in the setting. So basically, it's a big diffuse basalt aquifer groundwater system that we're dealing with. However, if we zoom in on it, and these are some well diagrams from the project area itself, we see a couple of things. First off, very deep cases and seals, 600, 700 feet of casing and seal in most of these wells. They're also very large diameter wells, so they're conducive for downhole control when we get there. But what we don't have, and we have a thick alluvial sequence on top, but it's silts and clays. So it's not available to act as a natural filter where we would take our source water from the Columbia River, run it through a sand and gravel filter, a naturally occurring alluvial aquifer, extract it and pump it down these wells. That is actually the process that several other ag irrigation projects have used in this region, but they have sand and gravel, we don't. In the wells themselves, though, down in our target zones down here, we have several water-bearing intervals. They are connected throughout the project area. That's good. And they are also confined, so we don't have a lot of interference or problems with the shallow water in this system. So we're dealing with these wells. We'll inject in one or more of these in the future. But first off, we do have to solve the anti-degradation problem, since that is a fundamental question to answer for the regulators to get this project to move forward. So to do that, we actually tested water throughout the system, starting at the Columbia River, which is where the source water would come through this pump station, be sent up through the pipelines several miles through booster pumps, etc., to about 10 miles from here into the wells that are part of this program. And we wanted to test throughout the system to make sure we understood both what's the surface water look like, the source water look like, is it changing in the pipeline, and then once it gets to the wells, is it any different than where it started, plus the groundwater system itself, what are the anti-degradation targets we have to meet. And what we found is it's pretty simple for us. Basically, the three things we have to deal with are iron, turbidity, and biologicals, bacteriologicals. We also did find it's also a seasonal problem. In the spring, when runoff is occurring, water tends to have higher iron, higher turbidity. In the fall, it does not. So we have some seasonality to our source water, which is going to affect how we treat our source water somewhere between here and here. So as part of that sampling program, we also recently completed, I should say, Carollo has recently completed a set of treatment tests using some field scale test beds. This is what the test system looked like in the lab. This is where it's set up next to this stack of filter tanks, water tanks in the field. Test the system like this because this farm is used to using artificial filtration systems. It's a technology they understand, it's a technology they use, it's a technology they can fix and maintain and operate on their own. So they're very interested in looking at, can they do this on a scale necessary to support the irrigated operation. So Carollo set up, in this schematic, just set up a filter test system to look at chlorine, coagulant, mixing, pressure, filters, to see, what would work. And they found out they could set up a pretty simple filtration system, sand and activated charcoal with a coagulant and chlorine addition that would get treat our water to a standard that would be acceptable in the anti-degradation context. At the same time, Carollo was working on that. We did some aquifer tests on this project to just double check and make sure that the hydraulics of the well and the aquifer are acceptable to would operate well in an AR injection scenario. And we found it would, but we also found that in a 3-day series, in any 3-day pumping test and recovery test, we actually get really nice recovery projected in the data. But this recovery kind of sends a false picture in that we know year to year water levels are declining. This recovery suggests we should come back to zero, which would be great, except we know from year to year operations that that's not happening. That we know the groundwater system is losing water out of storage. So that gets us to the scaling issue. Even though the hydraulics of the well and the near field aquifer are good and would be a great ASR target, and we know from the treatment test that it's doable, but at the scale of the problem, a large diffuse aquifer system that we know year to year is in decline, but we know on a short pumping test it is not, we now have a scaling problem, and that's the next piece of this project, is can the scaling problem be solved? And for irrigated ag, scaling is important because it's a commodity-driven economy. If the corn prices are down, wheat prices are down, whatever, if those prices are down, there's less money coming in the door. And if there's less money coming in the door, that means, can you do this? Or you have to ask yourself the question, can you do this? That differs fairly significantly from a municipal system, kind of a classic ASR system, where ratepayers, tax base, probably other government programs are available to help fund. This system, this program does not have that. So that's where we are at today, based on the treatment tests, based on the observed spring to autumn variation, based on the size of the aquifer, and in conjunction with changing water rights, changing the source of water, changing the farm practices themselves. Does AR make sense in that context from a cost-benefit point of view? And I think we see that throughout any irrigated ag environment. There are other ways sometimes to deal with these issues, and so cost-benefit has to be asked. Can they build this to treat for this in a cost-benefit scenario that makes sense to these guys? And they want to answer that question. And I give them a lot of credit for trying to figure out if it's doable or not. With that, thank you for your time, and have a nice day.